Our next speaker here will be a prolific author. Let me turn my camera back on. Bruce, you can turn your camera on as we introduce you so we can all say hi. He's a technology evangelist, a high-tech embedded consultant. He's produced quite a variety of books that we'll see in just a moment. And as I mentioned, we're going to be giving away a copy of his book, Real-Time Agility, later during the summit, so stay tuned. Hey, Bruce. Good to see you. Bruce works at MITRE these days and got some really cool experience in this area. So, Bruce, I'm going to hand it to you.
All right. Well, thank you, Arthur. Let me turn my webcam off so you can see my slides unhindered, let's say. All right. So, thank you, Arthur. I'm the Senior Principal Agile System Engineer at MITRE Corporation and the Principal at A Priori Systems. I have 40 years experience building systems, mostly in the safety, high reliability arena, aerospace, automotive, medical, nuclear, transportation, railway, and so on, various kinds of environments. So over the years, I've developed some opinions about what it means to be correct, what are the aspects of correctness. And that's what I'm going to talk about today, is what are the aspects of correctness and what it means to be correct. Okay, so first of all, let's focus on what does correctness smell like? When I say I'm correct, or the system is correct, what do I mean by that? Well, one of the things we mean, as Arthur pointed out, is compliance to standards. One of the nice things about standards is there are so many from which to choose to comply with. There are coding standards like MISRA, there are safety standards, other industry kinds of standards. Sometimes you'll have internal standards like your own coding standards, your own requirement standards and modeling standards, and so on. So one of the things we mean by correct is compliance to such standards. Okay. Another thing we mean is that it meets the requirements. So we have a set of, typically shall statements. System shall do this, it shall do that. Under these circumstances, system shall do that, and so on. So we mean that it complies with requirements. And certainly any notion of correctness would surely include the notion of meeting requirements. For safety critical systems, particularly, we mean that correctness, it doesn't cause harm. Now, just because it doesn't cause harm doesn't mean it actually delivers functionality. I have the world's safest car, a 1972 Plymouth station wagon, which I call the Hulk because it's enormous. Safest car on the planet because it has a safety critical state off, and it spends all of its time in that state, right? So it doesn't cause harm, but it's not providing functionality. But certainly part of what we mean by correctness is it doesn't cause harm. Another thing we mean sometimes is that it doesn't surprise us with unexpected and potentially bad behavior. So even in novel circumstances for which it wasn't perhaps originally intended, it does the right thing. We also think that it should meet the stakeholders' needs. So whether you're a driver or a maintenance engineer or a pilot or a gunner or a radio operator, you have needs. We all have needs, right? And the system should meet your needs with respect to the functionality provided by the system. Now note that that's not the same as meeting the requirements. There's actually an air gap between requirement statements and meeting stakeholder needs. If you look at a study that was done by the Department of Defense some years back, they found that 45% of the systems that they had created for them for in their acquisitions process could not be used for their original purpose. And a huge proportion of those were because even though the systems met the requirements didn't in fact meet the underlying need. So there's this air gap. So part of correctness is surely meeting the needs of the stakeholders that use the system. These days, We also mean resilience to attack, right? We'll talk a bit more about cyber physical security later, but I do a lot of consulting. I've consulted to well in excess of 400 projects. And many of those systems are worried about security for a variety of reasons. And in almost all of them, the approach to security is security, yeah, I need me some of that. And I find that inadequate, let's say, to meet the needs. So I'll talk about later about a process, a simple kind of workflow for how we can address security needs. But more thought needs to go into security and resilience to attack. But part of correct in the modern era of interconnected and IoT things is it's resilient to attack. It doesn't leak information. It can't be prevented from providing services. You don't want your cardiac pacemaker stop functioning because somebody had malware uploaded to it. That would be bad, right? So certainly resilience to attack is part of what we mean by correctness. Reliability is a stochastic measure of the availability of services supported by the system. And we want high availability. Now, I remember back in the days where if you bought a telephone and the seller said, well, and you only have to reboot this once a week, you'd say, I'm not going to buy that. That's a piece of garbage. Why would you have to reboot your telephone or reboot your TV? How bad is this system? Now, these days, we're more used to having to do that. But there are systems where reliability is key, particularly safety-critical systems, but other kinds of systems as well. The ability to deliver power to a community, the ability to provide telephone services. You expect high reliability of such systems. A part of correctness is meeting the reliability needs. And finally, you want good outcomes from use of your system. Bad outcomes should be avoided. So when we talk about correctness, we mean a variety of different things. Now, a key concept, or a set of concepts, is the notion of verification and validation, how we assure correctness of our systems. And I think that we mean three things. So I've thought about this, and this is the world according to Bruce. Thought about this, that one of the things we mean by verification is syntactic verification. A lot of times this has to do with compliance with standards, but we mean that it's well-formed, it's compliance informed. And this refers to aspects of functionality. We can think of functionality as the verbs of the system, verb phrases, what it does. Well, quality of service refers to how well those services are provided in terms of performance, reliability, safety, and so on, the ilities of the system. There's the structural aspects of the system, and then there's the behavioral aspects of the system, structure and behavior combining together to provide functionality with defined qualities of service. So there's a syntactic side. Does it comply with the forms we expect? And then there's the semantic side. The semantic side focuses on compliance and meaning. I mean, it should do this, even if it's not necessarily said the best. It actually does what we want it to happen. And this also has the same set of aspects of functionality, qualities of service, structure, and behavior. So syntactic verification is about verification of form. Semantic verification is verification of meaning. And finally, there's validation, which has to do with demonstration that meets the need, right? So something is valid if it meets my needs. And again, we have functionality aspects, quality of service aspects, structural and behavioral aspects of validation. Now, if we talk about syntactic, well-formed, this can be performed by independent two-way personnel. Compliance in form has a couple of forms, areas. One is about process compliance. So if you look at the various safety standards, DO 178, ISO 26262, IEC 61508, and so on, they have a number of objectives that have to be met. But they call out the notion of process. They don't define a conforming process, but to say your process, whatever it is, must meet these sets of objectives. And then you identify a process which maps to those objectives, and you get them to say, yes, that looks like a good process. But then you have to, when you enact the process, provide evidence that you complied with what you said you were going to do. You said you were going to do, and you demonstrated that if you did that, it would meet the objectives of the standard. And then you have to provide evidence that I did what I said I was going to do. And that's what audits provide. You provide the evidence of compliance of what you said you were planning to do. So audits are a necessary way of gathering data about compliance of your process and to your plan. And then for work products, we have looking at things that they comply with our standards in terms of the work products themselves. And there's two ways that we do that. One is syntactic review. QA personnel has their checklist, and they look at the work product, whether it's a model or source code or test cases or requirements, and they say, well, I've got all these characteristics that I'm expecting to see. Does it comply with those characteristics? In some cases, that compliance can be automated. And that's what we call static analysis. But specifically looking at compliance in form of those work products to the standards that they claim compliance to. For semantic correctness, this is compliance in meaning. This must be performed typically by engineering personnel and subject matter experts. There are three basic techniques by which we achieve compliance. One is semantic review. And again, I'm not just talking about code. My view of the university is larger than just code. It's all the work product we create. So you'll have systems architecture, you have requirements, you have test cases, you have plans and processes. All of those things should be semantically correct. And all of those things need to be verified to be correct in meaning. So it's not just about the code, okay? It's a broader means than that. So if we're looking at requirements, how do we say that our requirements are well stated? They cover the subject matter, they're complete, they're correct, they're not inconsistent. Well, the most common means is by review. We look at it. I've been on reviews of systems that had 20, 30,000 requirements. Those reviews are no fun. If you look at the Boeing 727, there are 200,000 requirements. Imagine being on that review, right? So you divide and conquer, but still, semantic review of work products is the most common means for doing some sort of semantic correctness assessment. It's also the weakest means. And the biggest problem is vigilance. You're pretty good for the first hour, 2 hours, 3 hours, but by the end of the day, end of the week, it's, oh God, kill me now, right? So most common, weakest form. The next step up is testing. Testing requires executability of work products. So testing of code is pretty common, but how do you test requirements? Well, if you've read any of my books, you know I'm a huge believer in modeling. So you build models of requirements that are in fact executable and executable. And then you can build test cases. The problem with testing is impossible to fully verify a system through testing because there is basically an infinite set of test cases. You can get arbitrarily close to complete at increasing levels of cost, but you never become fully complete. And finally, we can apply formal methods, which is the point. Formal mathematics, it's strong, it's hard to do in the general case of theorem proving, and it takes enormous effort. And I've done work with NASA GPL. We applied formal methods to a small percentage, 1 or 2% of the system design, because it's just too hard to apply it everywhere. It's just hard. But formal methods is kind of a static analysis applied to properties that you want to ascertain of the system. And finally, we've got validity. Does it solve the right problem? And again, the most common thing is to review. That's where we'll have customers involved, and we'll do things like classically SRRs, systems or software requirements review, PDRs, preliminary design reviews, CDRs, critical design reviews, where you look at something and say, yeah, that looks like it might be my need. Again, weakest form. You can also build executable models. So how do you know you've done a good job of requirements? You can build executable models and simulate those for various kinds of inputs and conditions to make sure that, yes, if it did this, that would meet my needs. That's what would be what I want. You can execute in a sandbox environment. You can do flight tests, and you can actually deployment, even if it's just partial functionality, you can deploy in the operational context to make sure it in fact meets the needs. So this gives rise to what I call the 12 degree of freedom model of correctness. As you've got 3 primary aspects, and within those you've got 4 dimensions of correctness. So that gives us 12 degrees of freedom. Now from a tester's perspective, your system is wrong until it's proven innocent. So developers and engineers tend to take the opposite perspective. Of course my system is right. I did it, I'm the kid, right? Of course it's right. Testers take the opposite perspective. Of course it's wrong. Let's go find the errors, right? And so the right perspective from a testing point of view or verification point of view is it's wrong until I can demonstrate that it's in fact correct. So let's talk about the levels of correctness. Now, the bottom tier kind of sort of works. You might do some kind of informal testing, and this is where the vast majority of systems and applications are. Kind of sort of works. I have some heartburn on this myself, but fine. The next level up is it works. And this is where we'll do some sort of rigorous formal testing. We might do, if you look at the 4 levels of testing called out by, for example, D178, where we've got structure testing, decision coverage, you've got MCDC coverage, and you've got data coverage. We've got those different levels of testing. This is maybe structured level coverage. This is where every line of code occurs and is tested in some particular test case. So you got coverage. And this is more than most people do right there, right? But that's only the second tier of correctness. Then there's works under all normal conditions. And you take into account all the edge cases, kind of exceptional conditions. So this is more coverage. This is more your DC coverage, at least DC coverage here. And that's additional levels of testing. And then works with invariant violations. That's where you've gone and explicitly done fault seeding, it's called, where you've broken things. I've, in fact, even during testing, I've pulled chips off boards and running systems to induce faults to make sure the system did the right thing in those cases, right? So you use values out of range, you break things, you violate all kinds of assumptions, and yet it still does the right thing in those cases. And the highest level is where you're still producing correct behavior, not having leakage of information or processes, even while being attacked by people at least as smart as you are. And that's the highest level of correctness in my book. And that's really, really very hard to achieve. So why do we test? Well, I think there are kind of 4 primary reasons why we do testing. The first of these is to find out, well, does it work? Then you find out if it doesn't work. And what are the conditions under which it doesn't work? Finally, uncover what are the limitations and constraints. What is the performance limitations of our system, for example? We may not know that until you test it and verify it. Well, under these conditions, this is our throughput or bandwidth, right? And finally, demonstrate compliance to various standards. So I think that at the high level, there are these 4 reasons why we test systems. But why is testing so hard, right? I remember back in the day, this is going back a few years, I had a manager who was arguing with me that design was in principle a bad idea. It's a waste of time, just write the code, what's wrong with you? 2 years goes by where we're having this argument, and he says, okay, I'm convinced that you should probably think about what you're going to do before you do it. But then you don't need the test because you thought about it. And that led to a whole other level of discussions, arguments. And the kicker is that we were designing cardiac pacemakers at the time, right? So that's kind of scary, right? Well, testing is hard. And we test because we don't know everything, and we discover things during test. There are many more ways a system can fail than succeed. There are not just one, but a small finite set of ways that a thing can be right. There's an infinite set of ways something can be wrong, right? Often there are implicit assumptions that are not explicitly stated, but you can invalidate those, causing failures. Therac 25 comes to mind, where we had this medical system delivered radiation therapy. And there are some assumptions, for example, that the user didn't press buttons too fast because they would tend to press the buttons because there's an annoying set of screens and people are just like, yeah, bang, 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 causing overruns of the buffer. And that led to failures, which killed people, right? That was an assumption made that wasn't explicitly stated. It is time-consuming and difficult to get degrees of test completeness, to test all the test cases. And furthermore, as we mentioned, people just as smart as you are trying to break your system, to steal information or to cause your system to fail. Let's consider a case. So here we've got some processing, and then we have three inputs, X, Y, and Z, with some range of values, in this case, just integers 0 to 9 for the three inputs, and there's an outcome or output of the system. Now you'd say there are 1,000 test cases, but it's more complex than that. What if sequence matters? What if the right order is Y, then X, then Z? And what happens if things come out of order? That may be important in your system. What if timing is important? What if you expect Z to occur in less than 20 milliseconds, but it arrives at 30 milliseconds? What if the output comes out too late? For example, you're controlling rudder of an aircraft, and if your output is too late, you get to unstable regions of your control space. Well, the plane crashes, right? So timing may be important. It may not always be late. There may be conditions under which you've got garbage collection or something else going on, which causes priority inversion. And so outcomes may come too late, right? So it may not happen all the time, just occasionally. And so only occasionally your plane crashes. What if the values inputs or the input values are not independent? If X is greater than 5, then Y must be less than or equal to 2. Can you constrain the testing space? What if we consider out of range values, X minus 1? And what if Z equals minus 20, does that fail in the same way as X equals 45? It may manifest different conditions and break in different ways. So you may have different test cases because they're not the same manifestation of the fault. What if only 2 values but not the third? What happens in that case? What happens if you run out of available resources like memory for the computation? What if other assumptions or preconditions are not met? So there are an infinite set of ways that the system can fail. So testing is hard. And then there's testing the validity of the system, qualities of service for various kinds of testing criteria. And there's a number of these, such as performance. Their performance is not just a number. It's a variety of properties of the system. In terms of execution time, worst case and best case, and worst case and average case are commonly considered. But also bandwidth and throughput are also aspects of performance that you might want to qualify and characterize in testing. For precision, something that's not often dealt with, you want to make sure you don't have accumulation of error during computations. So we have to not only manage our number of significant digits, which is called precision, but also the accuracy, which is conformance of an output to the specified value. So we're going to control a rudder to 30 degrees. Is 29.9 close enough? Or do I need 3 nines, 29.99 to be considered conformant? And fidelity is the precision of the input. How closely can I control the value? It might be plus minus 1 degree for control input, right? And that's what we call fidelity. And those are aspects of precision that are not commonly tested, but should be in many situations. Then we've got things like safety. So we've got the safety of the system. Sorry, screwed up. And I was going so well too. Safety of the system. Here we go. Here we go. Where we talk about the system shouldn't hurt people, shouldn't cause failures in ways that cause harm. And there's a variety of aspects of that. Same thing with security. We want to make sure our assets are secure against intrusion or theft or interference. We'll talk a bit about that in just a second. So there are a number of these qualities of service that we want to verify as well. So with respect to that, I'm going to spend the last couple of minutes and talk about, so how do I do safety analysis and come up with these various safety measures and safety test cases? So I've got a kind of a simple 7 action workflow for doing safety analysis. First, we want to identify what are the hazards. A hazard is a condition that leads to a loss. A hazard would be your brakes fail, and then the accident is when you hit the tree, right? So a hazard is a condition that leads to an accident or loss. And it's characterized by a number of properties, such as fault tolerance time, severity, how bad is it should it occur, the likelihood of its occurrence, and the risk, which is a product of those two values. Then we want to consider related conditions. So normal conditions, fault conditions, normal events, hazardous events, resulting conditions, and along intermediate steps in the processing. These related conditions. And those have to be described within the actions taken, the cause of the fault, current controls, detection mechanisms, and so on. The summary of this information is typically called a fault means and effect analysis, or FMEA. From this information, then we can create a causality tree, normally with a fault tree analysis diagram or some related means, where we identify the various conditions we've talked about in events and relate them with logical operators like and or and not and so on. So we look at what combination of events and hazardous events and conditions and hazardous conditions and faults, and how do they combine to manifest as hazards, to identify where in this causality tree we need to add our safety measures. And these lead to safety requirements and corresponding safety test cases. Now, similarly for security threat analysis, we want to reason about how secure is secure enough, what do we need secure against, and what do we need secure for. And again, security, yeah, I need me some of that is uninspired and I think inadequate. So I think we need to start off with assets. What are the features or properties that require protections? So we have notion of an asset and an asset context. So the asset might be the cache, and the asset context would be the safe that you put it in. And that forms then a security field around that asset. Then we can describe the assets in terms of various properties like the kind of asset it is, its availability, its value, which is important because we want to protect the more important assets at the expense of the least important. Then we want to discuss the vulnerabilities in the security field by which those assets or asset contexts can be penetrated, and then define the attack chains that penetrate those vulnerabilities against those assets. And there's this kind of canonical form for an attack chain, which is also known in some circles as a cyber kill chain, about how these means can be exploited. From that, we can create a causality tree, just like we did with the fault tree analysis, to identify the conditions, events, and how they combine to manifest as security violations, to identify where we want to have security relevant countermeasures. And this leads then to security relevant requirements, design, countermeasures, and test cases. So we talked about three different aspects of verification validation: semantic verification, compliance and form, and how we verify that using things like audits and static analysis and inspection. We talked about semantic correctness, and how we verify that using means like, well, semantic review, testing, and formal methods. And then we talked about validation, meeting the need, and how we validate that using, again, review, which is, again, the weakest form, simulation, execution in a kind of a sandbox environment, limited deployment, and flight tests as means to ensure that our system meets the need. If you want to know more, I've written on these topics in some detail. I have recently started up a YouTube channel. If you look for, go to YouTube and look for my name, Bruce Douglass. I'm still in the process of defining some of the channels within that channel. Also on my website, I've got a bunch of presentations and other information. You can download it. It's all free. You can go there and find stuff. With that, I'm a couple minutes over, taking up author's extra minutes that he gave me. I'd like to open the floor up for any questions that you might have.
That was great. It's always fascinating information. We do have a question that came in about what's the difference between safety, security, and reliability?
Yes, so that's a good question. It comes up a lot. If you look in German, the word is Sicherheit, which means safety and security. So it's actually not a distinction made in German for whatever reason. So a lot of times in the standards in German, they actually refer to the English terms because the German, in this case, is actually not adequate. So safety refers to freedom from harm, and security refers to resilience in the presence of attack, right? Freedom from intrusion, interference, or theft. And those are related concepts, but not the same concept. Another related concept is reliability. Reliability is a stochastic measure of the availability of services. And you can build a Venn diagram of those concepts, and they're not completely overlapping. They're points of interaction and intersection, but they're also points where they're not overlapping. In some cases, the safest thing you can do is shut the system off, which hurts your reliability numbers, but it still maintains safety of the system, provided that you have a fail-safe state. So they're related concepts, but they're not the same concept.
So there we go. Bruce recommends that everyone turn off all their computers and the world will be perfect. Well, thanks, Bruce. We appreciate it.